Now, for the triple integrals, to throw that into the mix here, what it turns out that these are helpful with are ones, triple integrals. Where do we want to use cylindrical coordinates? Well, it turns out triple integrals with involving cylinders, obviously because of the name, paraboloids, or cones are good candidates for cylindrical coordinates. All right. The conversion here, so if we've got a triple integral over some region E, and like we said, it's some E somehow involves cylinders or paraboloids or cones. Turns out in cylindrical coordinates, here's what it looks like. First of all, well, I better hold off on that. So we're going to R, thetas, and z's, right? Well, let's put the theta out here. So theta is going to go from alpha to beta. Then usually our radius is somehow a function of that, so function of theta. So let's call it h1. They call it h1 theta, h2 theta, and that leaves the z's, which usually z is written as a function of x and y. But since we're in polar, x and y are r cosine theta, r sine theta. And so z, we're going to write that in terms of a function, which is xy, but in convert those to polar. R cosine, R sine, and then the second z in terms of x and y, so it's in terms of r sine theta, r cosine theta, r sine theta. Okay. Usually works out if we're talking about these. All right, and so then, of course, our function, we need to rewrite it in terms of cylindrical, so it'd be f r cosine theta, r sine theta, z. All right. And then, what about our dv? Well, just like with polar, we had to add that extra r. It was r dr d theta for dv. Same thing for cylindrical. You need the extra r. Whoops. The order is. Yeah. You still kind of got polar. So, it looks bad, but it works out usually pretty well. Okay? Okay, so let's try one here. All right, let's evaluate triple integral over E y dv, where E is the region below the plane z equals x plus 2 above the xy plane and between the cylinders x squared plus y squared equals 1 and x squared plus y squared equals 4. So we've got it, yeah, you've got it bounded by that plane, whatever it looks like, in the xy plane, but you've also got it bounded on the sides. So you've got cylinders, so you've got, kind of got a shell. Kind of a weird thing. But I'm not going to try to draw it, no. All right. Okay, well, what we need to do is, of course, work on the R's and the thetas and the Z's. Let's start with Z, okay? Because we've got Z. Basically, Z is going between the xy plane, which is the xy plane, which is z equals 0, right? And z equals x plus 2, okay? And so if we just write it in those terms, in just rectangular terms, it'd be 0, z to x plus 2. Well, what would that be in cylindrical? Yeah, just 2. X is r cosine theta, right? So z would be r cosine theta plus 2. Z is between 0 and that. That's not too bad. That would be the first part, the first limits. All right? Okay. All right, so now let's think about R and theta here. Well, that's basically these, isn't it? We're trapped between those cylinders, and so you just think about one level of it here anyway. The x squared plus y squared equals 1, and just the xy would just be 2 circles, right? Radius 1 circle and radius 2 circle. And so I want theta's first, okay, so theta would go 0 to 2 pi. R is between 1 and 2, yeah. So that's not too bad. Let's see what the triple integral, though, what we run into there. Okay. So, didn't really set this up right to show you, but okay. So let's. I think we can handle that. All right. So the integral, triple integral over region E here, would be then, well, we know thetas are going to go from 0 to 2 pi. The r's from 1 to 2. And then the z's are from 0 to r cosine theta plus 2. Possibly, yeah. All right, now we need to rewrite our function in terms of cylindrical. So it's y, so that would just be what? R sine theta. And then the dv, don't forget your extra r, and then we're doing dz, dr, d theta. It's the usual way, because like I said, sometimes the r depends on the theta, also the theta variable, so that's why we usually choose to do the r. In this case, I don't think it would matter, right? Yeah. So the first one, we're just integrating with respect to z. So it'd just be r squared sine theta. There's no z in it, so it'd just be r squared sine theta z, and then z goes from 0 to, so won't it be this? R squared sine theta times z, which is z0. It's not going to matter here, but amount to anything. But going to be that, our first integral. Okay, so let's go ahead and distribute. So 0 to 2 pi. All right, so it'll be r cubed sine theta cosine theta plus 2r squared sine theta. And again, with this, I guess there's a couple ways. Eventually, we're going to have to integrate the thetas. So we can go ahead and call that, sine of 2 theta equals 2 cosine theta sine theta, or sine theta cosine theta. And so sine theta over 2 is equal to cosine theta, right? Cosine theta sine theta. So this is a half of the double angle sine 2 theta. And that'll be kind of an easier way to integrate it. We don't have to do that right now, but yeah, because we're doing r next. I was just pointing that out. All right, so this is 1/2 r cubed sine of 2 theta. Well, integrate that with respect to r. That'd be 1/4 r to the 4th. So that's going to be 1/8 r to the 4th sine of 2 theta. Plus, integrating with respect to r, so that would be 2/3 r cubed sine theta. Evaluate that from 1 to 2. Let's see, what does that get me? Well, if we plug in the 2, we have 1/8 of 16, so that'll be 2 sine of 2 theta. Is that right? Plus 2 cubed, so it'll be 16/3 sine theta. Minus, we do have to work with the lower limit this time, 1/8 sine 2 theta plus 2/3 sine theta, or minus. So we got 2 minus an 8, so that's 15/8. 15/8 sine of 2 theta. And then the sines would be 16/3 minus 2/3, so that'd be 14/3. Yeah, so this pretty easy one. Just let that u be u, so du would be du over 2, so I've got another factor of 1/2, so that would be 15/16 sine of minus cosine of 2 theta. See where we get that? And then this would just be minus 14/3 cosine theta. Then we go from 0 to 2 pi. So we have the cosine of 4 pi. Negative 15/16 times 1. Cosine of 2 pi, also 1. And then you plug in the 0. Look at this. It's going to be 0. Okay. Yeah, because those plug in 0, you also got 1, so that's just 0. Well, I think it's because we chose to do the integral of y. If we'd chosen maybe another function here of some other sort, because we weren't really finding the volume of this region. We're integrating over that region with respect to the f of x, y. So anyway, yeah, we weren't finding the volume here. We were integrating over this, so it's a little different than finding the volume. Because the volume is not 0, but we integrate this function over that region. We get, Okay. All right, the other thing to do in this section is to think about if we have a triple integral in rectangular coordinates, we call it. Let's convert to cylindrical coordinates from that. All right, so the integral -1 to 1, the integral square root of 1 minus y squared, and then the integral x squared plus y squared to the square root of x squared plus y squared. And it's x, y, z, dz, dx, dy. Convert that to cylindrical coordinates. An integral with cylindrical coordinates, okay? Yep, definitely got... Now, let's go ahead and write out what our limits here are. The y is -1 to 1, of course. The next one's the x, so the x is between 0 and the square root of 1 minus y squared. And then the z is between x squared plus y squared and the square root of x squared plus y squared. So yeah, that's going to be the easiest conversion, because we want to change all these x's and y's over to r's and cosines and sines of theta. Well, we've got a pretty easy one for the z's, don't we? What would this be in terms of r and theta? That's just r squared. And that'd be the square root of r squared, so that'd be r, yeah. All right, so there's our z's. Now we need r's and thetas, don't we? Well, let's look at what this is in the xy plane. So y goes from -1 to 1, and the x's are from 0 to the square root of 1 minus y squared. What's that? Semicircle. Semicircle, so be the right side of the circle, unit 1, right? And nicely, we're just talking about this. Y goes from -1 to 1, so yeah, it's just the right side of a unit circle. All right, well, what we need from that then is r's and thetas. Negative pi over 2 to pi over 2 for theta, okay. Yeah, the r's just go from 0 to 1. Pretty easy, isn't it? Okay, so what does that mean for our for our triple integral here? So it'd be, we do r dz, dr, d theta. So the theta, so we're going to go negative pi over 2 to pi over 2, and then the r's go from 0 to 1, and then the z's go from r squared to r. All right, and then we've got the function is x, y, z. The z's okay, but I need to change the x and the y, don't I? That'd be r cosine theta r sine theta times z. And then it's r dz dr d theta. Yes. So that's what r cubed. There's our sine cosine thing, so we could do our change that if we want to. So we've got r cubed a half sine of 2 theta. If we do our cosine theta times sine theta is a half sine 2 theta thing times z dz dr d theta. Okay? I think, well, maybe they.
You would be able to pull out the constant 1/2, right, from everything.
Oh yeah, yeah. You could bring it out. And I haven't evaluated this out, so shall we try it? Because I just said convert it, but I think they do make it. Doesn't look too bad, does it? All right, so we've got negative pi over 2, 0 to 1. Yeah, first one we do is z, so it'd be a half z squared, so it'd be a fourth r cubed sine 2 theta z squared. Then we're going r squared to r, so that would be, go over here. Negative pi over 2 to pi over 2, 0 to 1. So yeah, we plug in the r, we have r to the 5th, so that'd be 1/4 r to the 5th. And then plug in the r to the squared, so that'd be r squared squared, so r to the 4th, so r to the 7th. Yeah. So it'd be minus 1/4 r to the 7th sine of 2 theta. And one other point here, because I could factor off the sine of 2 theta, couldn't I? I could separate these out because we could do that, but yeah. But you would do that? So yeah, we could factor off the sine of 2 theta, so we'd just do this, couldn't we? Factor out the 1/4 too. Yeah, so we could do that if we wanted to. Can't always do that. All right, so that'd be a half, negative a half cosine of 2 theta. All right, and negative pi over 2 to pi over 2 times this would be 1/24 r to the 6th minus 1/32 r to the 8th, 0 to 1. That's going to be easy. Let's see. So that'd be cosine of pi. What's cosine of pi? Positive 1? Cosine of pi is negative 1. Okay, thank you. And then minus cosine of negative pi. Same thing, isn't it? That's 0. You get a 0 again? I didn't realize that. So it doesn't really matter what this is, but it's 1/24 minus 1/32, so whatever that is, it's times 0. This is going to be 0. 0 again. I don't think that happens as much as it happened today. All right.